today's technical session, Untimed C++ HLS Level Up. It's going to be presented by Robert Havlik from Microsoft. He has extensive experience in both FPGA and ASIC development, analog physical design to RTL, high-level synthesis and verification with a focus on hardware acceleration. And I've had the pleasure of supporting him as my role as an application engineer for the last couple of years, and really excited to see all the powerful things that they've been developing to streamline HLS as a whole. So please give a hand to Robert Havlik.
Very good. All right. Thank you for the introduction. That was very nice. So yeah, as you said, I'm Robert Havlik from Microsoft, and let's go ahead and dive in and level up Untimed C++ for HLS. And I will say this work was done all in concert with the Siemens Catapult HLS toolchain. All right, so first, the game plan for the presentation. I'm going to first go over the goals of hardware abstraction and talk a little bit about what hardware abstraction and HLS is. And then I'm going to jump into a number of challenges that we see with HLS, and then talk about how we level up each one of those challenges. And then we'll close it out with a summary and leave some time for Q&A. All right, let's begin the journey. So, the goals of hardware abstraction. So, over the years, we've been being able to meet the needs of Moore's Law over time by giving us the ability to build bigger and bigger circuits more effectively. We've gone from analog and transistors, cells and schematics, to the RTL level, and then now the HLS level. And between the RTL and HLS is really we're talking about how we get there to that next level of abstraction. And in RTL, we think about RTL stands for register transfer level, right? So we think about how we move data between registers, and HLS I generally think about and sometimes call function-to-function transfer, where we're creating functions and tasks that are meant to be running in parallel, connecting those, and then enabling the Catapult HLS toolchain to build circuits out of those functions, efficiency, and extract parallelism from that sequential code. And just to make sure, yeah, HLS stands for high-level synthesis for people that may not be familiar. So given that's the next level of abstraction, what are the key goals that we're looking at in order to make this flow work? So first is to simplify and improve the end-to-end design process for pipeline parallel designs. And that's really like, we have to be laser focused on simplifying each part of the process, as well as improving development velocity and agility, as well as overall quality and reducing bugs. And do all this without adding additional complexity to the entire process, which can be a challenge. And so now this presentation, we're going to go through different challenges in Untimed C++ in meeting these challenges, and talk about some of the upgrades that we've done to Untimed C++ to face these challenges. All right. First challenge we encounter is C++ simulation. So the whole goal is to abstract hardware design using sequential code. And C++ is generic and imperative programming language. Imperative simply being it's describing what you're trying to do in a step-by-step fashion. Now, HLS technologies are based on con-process networks at the very core. And for simulating concurrency in con-process networks, the basic idea is to simplify the simulation process by using a run-to-completion model for threading, and in software design patterns, it's often called the actor model. And this enables simulating concurrency within a single C++ thread, but we find that this adds a number of limitations. And so here in the code example I show in block A, this is an example of a run-to-completion process. And you can identify the run to completion with the available checks. So those are basically gates that say, do I have the data available in order to run this particular function to completion? So once I start, I can launch it, do all the calculations, and guarantee I can return. But this ends up being fairly fragile, because even if we take this function and then make the second read conditional, this can all of a sudden add challenges to the code. And so if we look at the code on the right side, when we add the conditional, those available checks will only guarantee that the function can execute if this read is also present. And so we kind of get to a problem where, in many cases we should have been able to execute this function because we only needed that first read and we didn't have the second read. And this is one code example of many where things quickly get complicated and non-intuitive. And so let's look at now how we're going to address the problem. So enter C++ coroutines. So the simulation context we found can be improved using C++ coroutines. And so what are coroutines? So coroutines are part of the standard introduced in C++ 20, and they allow methods to natively suspend and resume. So for example, without coroutines, a caller would call a function, that function would execute, run to completion, and return. However, the coroutines adds native suspend and resume capabilities so that the function can be called. We can check, for example, if a channel has data, and that goes for either channel. And if it doesn't have data, we can just go ahead and suspend back to the caller and then resume at a later time when the data is available. And you have to realize that the Catapult HLS tool will generate the correct RTL for these types of patterns. It's just the C++ simulation hasn't been there to be able to correctly simulate that pattern that the RTL can generate in C++. So let's take another look at coroutines here. And so a key part of implementing that we found with enabling coroutines is keeping the code still compatible and consistent with existing run to completion designs. And a key thing is, like you saw in the previous code example, it enables us to remove all those if available calls, which avoids many simulation versus synthesis bugs. We find that even just those availables are non-intuitive to people new to HLS. So we can get rid of those and clean up the code and generally make the code more intuitive and avoid those differences between synthesis and simulation, which is also very important in keeping everything simple. And how we implemented it is it's compatible with existing HLS synthesis tools and flows. So we add all this capability for simulation, and then for synthesis, kind of a lot of that capability just kind of gets taken out because the synthesis engine can already handle these code patterns. We just had to put this in order to get the simulations to run correctly relative to what the design intent was. And so you can see, like, these are custom libraries that we added on top of C, and we did it in a way that we can keep the structure very consistent with existing HLS designs and run to completion. So for example, you can see here, like if we have, this is block AB is showing a hierarchical design where we're going to call block A and block B. And here I have block A simply running in a coroutine context, and then block B running in a run to completion context, and everything kind of just works in that familiar context for people already designing with HLS. so that the C++ declarative hierarchy and structure is clearly maintained, even though we've added this suspend and resume capability. All right. Next challenge along our journey, C++ hierarchy. So, again, System Verilog and System C are declarative in nature and natively have hierarchy support. But given C++ is just a generic programming language, the hierarchy support is not native. But when we design, hierarchy is an important aspect of managing design complexity. And the Catapult toolchain can back out hierarchy when we run the design through the toolchain. It does a great job at that. But in order to use the hierarchy, you have to wait until the point of running it through the toolchain. And so I just put an example here of a very simple, a simple set of blocks, like block A. I give block top, and then block top would have block A and block B. Block B would have block C and D. And kind of what that looks like in code from HLS designs is you have generally a class, and you call those two blocks, like block A and block B, internal to the top block, and that's kind of how you construct hierarchy. And you can see, again here we've added some changes to the code, like this macro on the top, and then also this macro in the middle here. But beyond that, that's all you really have to add to enable this feature. We try to keep everything as clean as possible, and keep the new features as isolated as we can. So in the previous slide I showed kind of what it looks like in code to add the hierarchy, and we found that we can actually add C++ hierarchy at runtime to designs that in a way that's really hidden from the programmer. So the programmer doesn't have to worry about managing the hierarchy. We just get the hierarchy integrated into the design. And so, for example, what this allows us to do is we could instantiate that block top from the previous example, and then print hierarchy, and at runtime the design knows what the hierarchy is, as well as what the connectivity is, and like what the ports are on the different blocks. And this turns out to be fairly useful in practice. All right, let's go on to the next challenge. C++ debug. And this is one, when I first started using HLS, I really wanted to be able to do, because a lot of RTL designers, right, you're used to debugging parallel designs in waveforms, and C++ is really its strength, right, is single-step debugging through the code. And the challenge with HLS, right, is we really kind of have a mix of those two paradigms. Like each individual function or block is really an imperative step-by-step block, but then we've connected the functions together in a declarative structure, and you really want to be able to debug at the kind of the function output level. But the challenge here is in Untimed C++, the waveforms are very impractical due to there's no clock reference in Untimed C, kind of because it's Untimed C, and then the order of design calls can influence what happens, and any block can really generate an arbitrary amount of data per call. So that makes it fairly hard to reason about in time what's happened, because all these factors kind of can blur what's actually happening, right? And you can change these factors, right, as you update the design. So how do we address this? And a key part of addressing this is using the capabilities the past capabilities we talked about, and then creating a waveform model on top of that. And so how we think about this is we create a deferred write model for channels where each block can be conceptualized as a single sequential element and kind of one call through all of the blocks we think of as one cycle. So you give every block a chance to execute, and we call that an iteration. And basically at the end of each iteration is one write is committed for each block. So you can pretty much think about, in this context, each of the HLS blocks basically becomes like a sequential register that has non-blocking writes. So you can basically run your design, and then with this infrastructure, reason about what's happening in time, regardless of how you implemented the underlying functions. And so with this functionality, we can use our hierarchy to actually export the known hierarchy, since we have that information, to the waveforms, and then use this waveform model in order to create coherent waveforms that we can then debug at basically the function boundary level. All right. So now we've solved that problem. The next one is the RTL and UVM integration challenges. So when we're abstracting, there's almost always a reason that we have to interface back into existing RTL as well as UVM test benches for verification, as well as system Verilog test benches as well. And really, at the end of the day, when you're integrating with these environments, you can use the generated RTL, but when you're in these test environments, you want to be able to test your source code instead of the generated RTL, right? Because debugging the generated RTL is, again, just adding additional work that you didn't want to deal with, because you kind of have to back out, like, what did the tool do? With the Catapult tools, debugging the generated RTL is generally not that bad, because there's very nice traceability back to the RTL, but still not ideal. And I will add, there are many options for bridging between like C++ and System Verilog and UVM, and we've explored a number of those in the past, and here this solution will focus on using System C. So how do we level up this problem? So given the hierarchy that we talked about, we have the information now in order to be able to generate the System C wrappers in order to enable integration with existing RTL as well as UVM or System Verilog test benches. So what we do is we go ahead and, like, whenever you run your test, we just add a function call that creates a separate folder that builds a transaction level wrapper around the untimed design. So the untimed design will be interfacing with channels, and then we create a wrapper that bridges it to the connections library. And then we build, and then this basically creates a transaction level wrapper in System C. So you can use, at this point, System C at a transaction level. And then for RTL integration or System Verilog integration, we create a pin level wrapper around that takes the connections and breaks them out into the specific pins with ready valid interfaces. And then when we generate the pin level wrappers, we also generate test infrastructure around that to validate those wrappers actually work and produce the same results as the original design. So we'll take the original C++ test bench that you did and then replay those inputs to the pin level design, and then check the outputs that were done in the Untimed C test bench on the output to basically validate that this pin level System C wrapper works. And that same process is also done for the transaction level wrapper as well. So with this, you can keep the wrappers and interfaces consistent with your design, and they evolve with your design as the design changes. So every time you run a test bench and validate the design works, you can get your interface in order to integrate with RTL. Yeah. And this effectively allows the designers to stay in the untimed C realm, which is super key, and avoid having to go into the system C. Right? We're still using system C. We're just getting it automated. All right. So our level up has been achieved. It's been achieved through improving the simulation context of Untimed C++, the hierarchical awareness, the waveform debug on Untimed C++ code, and the wrapper and wrapper test generation. And these enhancements ultimately enable simpler, cleaner code, new design patterns, and this is a deeper topic, pretty much another presentation, but when you have those coroutines enabled, you can really do a lot more with Untimed C++, where conventionally you'd have to go and kind of transition to a system C-based design. It really expands the reach of what can be done in Untimed C and what kind of designs you can express efficiently and simulate correctly in Untimed C. Because really you want to move as much testing as possible as well into Untimed C and carry that forward. And then addition, right, we bring the debug methods, right, the waveform-based debug that RTL designers are used to into the Untimed C space, and then on top of that enable the simpler integration into the RTL world. So this effectively allows us to be able to take the generated RTL, and we have basically now a pin level wrapper that looks just like the generated RTL, and so we can switch out the source and go back and forth if we find problems to figure out where the problem is in the process. All right. And then the credits, would like to thank everyone on this development. The AEs and the Catapult team have been incredible as far as supporting us. The people at Microsoft working on this, advancing the state of the art, as well as Copilot for the presentation graphics, and the UTU organizers and sponsors for making this all happen. And finally, the next steps and call to action is really like finding a way to standardize these methods and libraries, right? So like there's quite a bit of work that we did here, that's fairly difficult and outside of the pure standards for HLS synthesis, but kind of getting those out there and used and actually part of the design and part of the Catapult tool as well. Like there are extensions where if the tool chain actually expects some of the stuff that we're doing, we can actually even do more. And then as well as capturing new design patterns and capabilities enabled by these features and functionalities, and even bringing some of the debug features we talked about into the simulators and debuggers, right? Because the simulators and debuggers can handle System C and Untimed C, but being able to have more native HLS awareness would help with both the integration as well as making things smoother for RTL designers to transition to using this as powerful design abstraction technology.